Hi, before we start with our presentations, I would like to introduce myself. So my name is Engku Aridiana binti Engku Muhammad Azhari. My metric number is 208050. For today's class, which is fluid mechanics, we're going to present two topics, which is fluid properties, and the other one is dimensional analysis and modeling. So we go to the first topics, which is fluid properties. So we have to know the basic of it. So what is fluid? Fluid is a substance that flow and can be liquid or gases. A fluid cannot support a shear stress without moving, and a fluid at rest has no shear forces, only pressure forces. So for the introductions to fluid properties, the first one is density. So the meaning of density is the ratio of mass of fluid to the volumes of fluid. So this is the formulas of density, which is mass over volume. Number two is specific weight, which is the amount of weight per unit volume of a substance. Number three is specific gravity, the ratio of the density of a substance to the density of water at 4 degrees Celsius, the ratio of specific weight of a substance to the specific weight of water of 4 degrees Celsius. So this is a formula for the specific gravity, which is the density of substance divided by the density of water at 4 degrees Celsius. So number four is surface tensions, which means the density of liquid surface to shrink into the minimum surface area possible. So the formula for the surface tension is force divided by length. So number five, viscosity, which means a measure of its resistance to deformations at a given rate. So this is a formula for to find viscosity, which is 0.0168 times density times temperature power of negative 0.88. So next is Newtonians and non-Newtonian fluids. So first, what are Newtonian fluids? So where stress is Newtonian fluid is where stress is directly proportional to rate of strain or fluid with the constant viscosity at the fixed temperature and pressure. A Newtonian fluid's viscosity remain constant no matter the amounts of shear applied for a constant temperature. These fluids have a linear relationship between viscosity and shear stress. They obey the Newton laws of viscosity, which is this is a Newton law of the viscosity, and this the formula of it. And typical Newtonian fluids include water and thin motor oils. So this is a graph of Newtonian fluid. So what I'm going to talk about this graph is that for graph A shows that the relationships between the shear stress and shear rate is a straight line, while graph B shows that fluid viscosity remains constant as the shear rate is varied. So for example for the Newtonian fluid is water, mineral oil, gasoline, and alcohol. So next is what are non-Newtonian fluids. So non-Newtonian fluids is where stress is proportional to rate of strain, its higher powers and derivative, basically everything other than Newtonian fluid. So non-Newtonian fluids are the opposites of Newtonian fluids. When shear is applied to non-Newtonian fluids, the viscosity of the fluid change. A non-Newtonian fluid is broadly defined as one for which the relationship between shear stress and shear rate is not constant. It means that there is non-linear relationship between shear rate and shear stress. In other words, when the shear rate is varied, the shear stress doesn't vary in the same proportion or even necessarily in the same direction. So for example, to this fluid is soap solution and cosmetic food such as butter, jam, cheese, soap, yogurt, natural substance such as lava and gum. The behavior of the non-Newtonian fluids can be described in three ways, which is dilatant. Viscosity of fluid increase when shear apply. Second is physiodoplastic. The more shear applied, the less viscous become. And the third is generalized Newtonian fluid is viscosity is constant, stress depend on normal and shear strain rates and also pressure applied on it. So this is graphically differences between Newtonian, physiodoplastic and dilatant, which is both is non-Newtonian fluid. So we can see the difference between graph. Next is surface stress. So surface stress defined as a tensile force acting on the surface of a liquid in a contact with air or between two immiscible liquid. Surface tension allows insects, usually denser than water, to flow and slide on a water surface. And its unit is N per meter power of 2, and surface tension has the dimensions of force per unit length or of energy per unit area. So surface tension is basically like insects that is float on top of water, you know. So the effect of temperature on surface tension is by increasing the temperature of a liquid result in increasing the kinetic energy of the molecules, thereby decreasing the intermolecular forces. So the inward forces acting on the molecules of the first layer of the liquid decrease. In other words, by increasing temperature, the surface tension decrease. So stress is defined as the force per unit area of a material. So this is the formula of the forces, and this is unit for the stress. This is a formula for the stress, and this is unit for the stress. Next is strain, which is defined as extensions per unit length. This is the formula to find the strain. Next is elastic modulus, which is mean as a property of an object or material which will restore it to its original shape after distortion. So this is the formula to find elastic modulus, which is you have to find stress first and strain, and then divide both. Next is compressible and incompressible fluid. So for the compressible of liquid, compressibility is the change in volume due to change in pressure. The compressible of liquid is inversely related to its volume modulus of elasticity, also known as bulk modulus. So the symbol for the compressibility is like beta. So this is the formula to find compressibility. So the compressibility modulus is the reciprocal of bulk modulus. Liquid and solids are relatively incompressible. They have large values of beta, compressibility. On the other ways, the density of liquid and solid is relatively constant with pressure changes. Gases are easily compressed, and the value of compressibility are strongly dependent on pressure changes. The density of gases depends strongly on pressure change, beside of change in temperature. So next is vapor pressure. So vapor pressure is the partial pressure produced by fluid vapor in an open or closed container, which reach its saturate conditions, or the transfer of fluid molecules is at equilibrium along its free surface. In a closed container, the vapor pressure is solely dependent on temperature. In saturated condition, any further reductions in temperature or atmospheric pressure below its point will lead to the formations of water droplets. Boiling occurs when the absolute fluid pressure is reduced until it is lower than the vapor pressure of the fluid at the temperature. So next is dimensional analysis and modeling. We're going to talk about dimensional analysis and modeling. So first is dimensions and dimensional homogeneity. So what is dimension? So dimension is a physical property which describes a way any physical quantity is related to fundamental physical quantities. Next is what is dimensional analysis? So dimensional analysis is the analysis of the relationships between different physical quantities by identifying their fundamental dimensions such as length, mass, and time. So first we're going to talk about dimensional homogeneity. So dimensional homogeneity means the dimensions in each equation on both sides equal. So the law of dimensional homogeneity is every additive term in an equation must have the same dimension. So for example, let us consider the equation for this equation. So V, the units for V is LT power of -1. The same goes to formula for this is also LT power of -1. Make sure each equation on both sides is equal. Dimensional analysis and similarity. So in most experiments, to save time and money, tests are performed on a geometrical scale model, not on the full-scale prototypes. In such cases, care must be taken to properly scale the result. Those powerful technique called dimensional analysis is needed. The primary purposes of dimensional analysis is first is to generate non-dimensional parameters that help in the design of experiment and in the reporting of experimental result. Second is to obtain scaling laws so that prototypes performance can be predicted from model performance. And the third one is to predict trends in the relationships between parameter. In a general dimension, dimensional analysis and similarity is in a general dimensional analysis problem. There is one pi that we call dependent pi and also independent pi. So the principle of similarity is, first one is geometric similarity, which is the model must be the same shape as the prototype but may be scaled by some constant scale factor. Second is kinematic similarity, which is the velocity at any point in the model flow must be proportional by a constant scale factor to the velocity at the corresponding point in the prototype flow. The third one is dynamic similarity, which is when all the forces in the model flow scaled by a constant factor to corresponding forces in the prototype flow, which is force scale equivalence. Next is the method of repeating variables and the Buckingham pi theorem. So how to generate the non-dimensional analysis? So there are several methods, but the most popular was introduced by the famous one, which is Edgar Buckingham, called the method of repeating variables. So this is a concise summary of steps that comprise the method of repeating variables. So we go step by step. So the first one is step 1, which is list of relevant parameter. And step 2 is list the primary dimensions of each of the n parameters. So step 3 is set the reduction as the number of primary dimensions, calculate k, the expected number of pi. You can see here, this is step 3, which is the number of primary dimensions in the problem, or then the number of pi predicted by the Buckingham pi theorem is this. And step 4 is repeating parameter. They have a few cautions for this step, which is number 1 is never choose dependent variable. Do not choose variable that can form dimensionless group. 3, if there are 3 primary dimensions available, must choose repeating variable which include all 3 primary dimensions. Number 4, don't pick dimensionless variable, for example radian or degree. Number 5, never pick 2 variable with same dimensions or dimensions that differ by only on exponent, for example these two. And number 6 is pick common variables such as length, velocity, mass or density. Don't pick less common, like viscosity or surface tensions. So this is step 5, which is we have to construct this and manipulate as necessary. And this is step 6. Step 6. What is step 6 is write the final functional relationship and check your algebra. So last but not least is dimensionless parameters. So in a dimensional analysis, a dimensionless quantity or quantity or quality of dimensions. Quantity or quantity of dimensions. One is a quantity without an associated physical dimensions. It is thus a pure number and as such always has a dimensions of 1. So the other example of dimensionless quantity, for example Weber number, Mach, Darcy friction factors and drag coefficient. So that's all for my presentations. Thank you.